All right, guys. One thing I want to talk about today, I want to go back and review. Matter of fact, let me just kind of get out of this for just a second, and let me actually pull up the periodic table because I want to go back and I want to review some of the high points that we've talked about thus far. All right, so right now, let's focus on Group 1. What are some facts we know about Group 1? All right, I had a feeling that was going to happen. I was going to start yelling. All right, what's its name? Alkali metals. Okay, alkali metals is Group 1. How many valence electrons does it have? What does it want to do with that one? Get rid of it. So what does that mean its charge is? +1. All right, so we know that. What do we know about hydrogen? Yes, it's technically above on top of Group 1, but does it really belong like with its properties? No. What is the only reason that it's in Group 1? It's got one valence electron. That's the whole entire key of the reason why it's sitting right there. Now, what is it? Are all of those metals really, really reactive or not reactive at all? Very reactive. As you go from top to bottom, what happens to their reactivity? It increases. What group do you think they really love to react with? Why 17? Okay, all right, so let's talk about that. I heard a few good things. Let's talk about its name. What is the name of Group 17? The halogens. What? How many valence electrons? And don't you say 17? 7. 17 has 7. Okay. What does it want to do with an electron? Gain 1. So its charge is -1. So we have the +1 group and the -1 group coming together. What does a +1 and a -1 do? Cancel out. So that compound that they're going to form when they bond is going to be neutral. Very good. Or stable. Both things are true. Now, is that group really reactive or hardly reactive at all? Very reactive, just like Group 1. However, Group 1 are very reactive metals. Group 17 are very reactive what? Non-metals. Very good. All right, so let's go back over here to Group 2. The name? Alkaline earth. Okay? Alkaline earth is its name. How many valence electrons? 2. Charge? 2 plus or +2, same difference. Now, whenever we were doing electron configuration, what did we have to do with this helium? We had to put it over here. But why is it not normally over here? Because let's talk about helium for a second. We just said that Group 2 has 2 valence electrons. Well, how many does helium have? It's got 2. Well, why is it not right here? It's full. That's the key. What do we know about this group right here? They're all stable. They all have that full outer valence electron shell. So that's why we put helium over there. That is the only characteristic that helium has in common with Group 2. Everything else is going to be completely different. All right, so now we talked about Group 2. Now let's talk about a different group. Let's talk about Group 16. How many valence electrons? 6. How many, what does it need? What, in terms of electrons, what does it do? It gains 2, so its charge is -2. Very good. We don't really have a name for that. That's just the oxygen family. All right, so far we said that we have 1 valence, 2 valence, then we had 7 valence, and we had 6 valence. So let's talk a little bit more. We've kind of hinted around it, but when we said that noble gases are full, how many do they have? 8. What's the only exception? Helium, and it has 2. That's the only exception there. Well, so far we kind of have a trend going. We have 1 and 2, and then we have 6, 7, and 8 going. Does that make sense? Well, now let's look at 3. Or excuse me, at Group 13. So this is Group 1, 2, and this really is Group 13. How many valence electrons do you think it has? It's got 3. Very good. And if I were to draw boron, you would see that it has 3 valence electrons. All right, so let's skip on the other side. What about nitrogen? What do you think it has? 5. Okay, well that would leave the middle group right here as how many? 4. There's a reason I did that. So let's go back and let's add another little fact. What's the charge of Group 1? All right, so we said +1. What about Group 2? +2. All right, let's go all the way to the other end. What about 18? Is there a charge? No, so it's just going to be 0, right? What was 17? -1. 16 was? -2. All right, well, let's think. This kind of goes back to everything we've talked about. We know these two. Our Group 13 has 3. How many can it have up to? 8. So is it easier to gain 5 or lose 3? Lose 3. So what do you think it's going to do with these 3? It's going to give them away. So do you agree that group 13 would have a positive 3 charge? All right, well, let's go back again and let's look at nitrogen. Nitrogen has 5. Is it easier to lose 5 or gain 3? So what do you think it's going to be? It's going to gain 3. It's going to turn into negative 3. So here's the issue. What about group 4? What does it do? Do you think it gains or does it lose? It actually does both. It's plus or minus 4. What is the top atom in that entire group? Carbon has its own branch of chemistry called what? Organic chemistry. This is why. What can it do? It can do a lot of different things. So this is why carbon has its own entire chemistry subject devoted to it, because it can do so many different things. Our body, if besides water, what's the most important compound? Carbon. Absolutely. We're very, very, very high percentage of carbon, because without carbon we wouldn't have life at all, period. Everything would be dead. Nothing would be living without carbon. So it's amazing how the entire periodic table is built, but one of the most important things to us is carbon, because without carbon we wouldn't have life. Those of you that are really into like aliens or whatever, have you ever heard that other life forms may not be carbon-based, but they may be what? Have you ever heard of silicon-based life forms? Yeah. Okay. Silicon-based life forms. Why do you think they say it may be silicon-based? It's the exact same group as carbon. That's why. So if you ever hear of those things that say, well, on Mars or on Jupiter or different universes, there may be other life forms, but they may be silicon-based, well, that's the reason why. It's because it acts just like carbon. Now, also in that group, you've got SN and Pb. What is SN and Pb? I don't think there's anything out there made of tin and lead that's living. That's weird. Okay. So yes, it is in the same group, but what we're going to come to learn is that the D block actually kind of looks like an upside down state of Tennessee. You'll see what I'm talking about? It kind of has this downward little slope. So yes, the D block ends there, but it actually kind of includes well, it's not wanting to draw. It actually kind of includes these metals right here, even though they're not a part of the D block. Again, I just kind of wanted to point that out to you. So those are the characteristics of the periodic table that I wanted to talk about so far. So now let's kind of get into some other things that I want to hit today. Now, we're going to talk about trends. We've already talked about trends. Your valence electrons, what happens as you go left to right? They increase. Your charge, it goes up until you get to 14, and then what happens? It starts going down. So it's a plus or minus game there, okay? So let's just kind of talk about this. I don't think y'all have this slide, right? Do y'all? Okay, all right. So describe some trends that you can observe, such as fashion. So let's stop right there. What are some fashion trends of today? Polo? Lace? Socks. How many of you have on lace socks? I have to see them. Yeah. Pizza socks. I can't see it. All right, Chacos. Fair? Okay. Vest. I think vests are in now. Vest. Kohans, vest. Scarves. Those are huge nowadays. Flannels in now. Leggings. Those are in. Thank God Uggs are out. Oh, but they are. If you wear them, you'll be made fun of. Riding boots, those are kind of trending maybe down. Those are trending down. Anything else that I'm not cool enough to know about? You are getting weirder and weirder by the second. So again, those are some things with fashion. Behavior and color. Is anything big color in right now? Colors have black is always just one of those, okay, all right. Designs, we know that housing, you can drive through neighborhoods and you can tell exactly when that neighborhood was built based on the design of the house. And then foods, anything trending food-wise? Pizza's always in. Chinese food. The organic thing, the yogurt thing was a crave for a while. Bagels was Starbucks is always in. So again, the whole point about it is we can sit here and we can talk about for hours how things trend. How you can look back, acid wash jeans are, I don't know who's bringing them back. They need to stop. But they're for some reason coming back. I have seen what we used to call wallabies are slowly starting to come back. But see, and probably your parents are a little bit older generation. They called them hush puppies, and so it went from hush puppies. We called them wallabies, and what do they call them now? They're kind of like the gummy bottom shoes. Again, I used to have some Clarks or Crocs. So, again, how are trends used to classify? We can classify. So here's the deal. Yes, there are trends in life outside of this classroom, but there are some trends inside of this classroom. We're talking about 5 of them. The 5 we're going to talk about are atomic and ionic radii. Let's pause right there. Is an atom and an ion 2 totally different things? Do y'all have this slide? Okay. All right, do me a favor. Above the word ionic, I want you to write something. I want you to write charged. And then write and then write that. It's charged, and why is it charged? Is it not more? It's just a different number. Okay, it can be more or less. Okay, it can be more or less different number of electrons. So atomic and ionic, those are 2 totally different things, but they each have a radii. Now, what is the word radii? That's plural for radius. Now, what is a radius? Half the diameter of a circle or a sphere. Here's the issue that we're going to run into. Are atoms spherical? In a way. But here's the issue. Can I know exactly where the nucleus of an atom is? Yes. Here's the problem. Do I know where the outermost part of an atom is? That's the problem. It's this haze. It's this electron cloud. And we're going to talk about how we can define the radii based on that. We're going to talk about ionization energy, electron affinity, and electronegativity. Yes, all those are weird words, but we're going to define them once we get to them. Today we're going to just talk about a few other things. Okay. Now, before we get into those deeper concepts, we have to understand the underlying concept of what makes these things, or what makes these trends happen. The word you all need to understand is Zeph. Okay. We've discussed Zeph before, but this is what I want you to do. Underneath this picture, do y'all remember this thing? Okay. What did the letter A represent? Mass number. What does the mass number give you? Or how do you get it? So protons plus neutrons. Alright, everybody okay with that? Protons plus neutrons. Z. What is Z? Very good. The atomic number. Alright. What does the atomic number tell you? Very good. Number of protons. And where are the protons? Very good. In the nucleus. So let's talk about how this little thing that we just wrote translates into Zeph. First of all, again, what does the letter Z stand for? The atomic number. So that's Z. The atomic number is the number of protons. What does EFF stand for? Effective. Okay? So effective nuclear charge, or Zeph, is how effective that nuclear charge is on an atom. How effective the nuclear charge is on an atom. Now let's pause. What are the 2 things in the nucleus? Protons and neutrons. What is the only thing in that nucleus that has a charge? Protons. So really, the effective nuclear charge, the charge is coming from what? Very good. So what we're really going to focus on is the number of protons. That's what we're really wanting to see, is how powerful are those protons on that atom. What are the protons trying to hang on to? The electrons. So here's the example that I'm going to run with throughout the entire theme of this lecture. Let's pretend that we go up to Slingler for just a second, and I take you outside on the playground, and I send 10 kindergartners out. You going to be able to watch them all? Good luck. So here's the perspective that I want to talk about. Let's look at this picture that we have. Where's the nucleus in this thing? Okay, do y'all see that little dark purple orb right there in the center, the little small one? All right, this right here is the sodium nucleus. And in the sodium nucleus, how many protons do we have? We got 11. It says 11 right there. It's atomic number of 11. So here's the deal. What we're going to have to do is we're going to have to try to maintain and balance this atom so that the protons in the center have the ability to hang on to all those electrons that are running around outside of it. Now, this blue little orb, what I want you to highlight those, these are called the core electrons. What does it mean to be a core electron? In the center, it's in the middle, it's closer to the nucleus. Well, here's the deal. What group is sodium in? It's in group 1, so it has how many valence electrons? So we have 1 valence electron. You see it out there all by itself. What do we know that sodium wants to do with that 1 valence electron? It wants to give it away. So let's go back up to Slingler for just a second, and I send you out there with 11 kindergartners, and I say, watch them all. Would it be okay if you lost one of them? Not to that mama and daddy. However, in this case, what if I take 10 of the 11 and I make them run around you and screaming and yelling and hollering and try to knock you over? Would it be more difficult for you to maintain and watch that one that's climbing over the fence behind your back? Because they're probably going to do that. They're going to somehow manage to take your attention and distract it away from that one. You with me, Devin? You sure? Okay. Sorry. So what's going to happen are these 10 core electrons are going to do something. I want you to highlight this word. They're going to screen. What's another way to say screen? Huh? Block, maybe. The word I want you to write under the word screen is the word shield. So if you've got 10 kindergartners running around yelling and screaming right around your feet, are they going to shield your viewpoint of that 11th one? Yes, so here's what's going to happen. These 10 block your viewpoint. So what is going to happen to that 1 valence electron out there all by itself? It's going to go away. So this one is going to go somewhere. Well, once you get rid of it, who do you think is going to come along and take it? That's weird. Talking about electrons. One of the halogens. Perfect. Very good. One of the halogens is floating around out there looking for this guy. Okay? So that's what's going to happen. So each of the 11 electrons is attracted to the positively charged nucleus. Why are the electrons attracted to the positive nucleus? Nate, opposites attract. What's the charge of an electron? Negative, and positives and negatives attract. Perfect. So that's kind of the diagram that we're going to be focusing on. Okay. The charge experienced. Matt, you with me? You need to get on the notes, please. You with me, Jay? Okay. A charge experienced by an electron on many electron atoms. Now, we're not going to have to work with any of this math, but I want to show you there actually is a little bit of the math that's going to help in just a second. Z is the atomic number. And again, what's the atomic number tell you? Very good. So really what we're working with here is the number of protons. S is the screening constant. Since it's a constant, what does that mean? It's always going to be the same. It's going to be the same for every atom. Or excuse me, it's going to be the... Does that make... Like... Carbon is going to have a different one than oxygen, and oxygen is going to be different than fluorine. Every time you have the same element, it'll be the same one. Okay, so S is the screening constant, usually close to the number of inner electrons. What is the name for inner? Core, very good. So do you agree that sodium has a different number of core than fluorine does? Yes, okay, so that's kind of what we're looking at here. All right, so let's go from this perspective. Now, the effective nuclear charge is not the same as the charge on the nucleus. Guys, this right here is important. Zeph is different than the charge on the nucleus. Where does the charge on the nucleus come from? Very good. So it's completely different. So that's going to come from the protons. Electrons are attracted to the nucleus. Why? Negatives and positives always attract. However, electrons repelled by electrons that screen or shield it from the nuclear charge. This screening or shielding is going to come from which group? That core. Okay? It's that little group that's inside. It's not on the outer shell. Okay? Nuclear charge experienced by an electron depends on two things, and this is really important. Put a big star beside these last two. The charge experienced depends upon two things. Distance from the nucleus. Okay? If I take 11 kindergartners and put them in this room, do you think it will be a manageable feat to control them? A manageable feat. All right, now let's compare it to something. What if I take you and I put you into the commons? What have I done to my area? It's much bigger. Is it a lot harder to maintain those things? So here's the thing. As the distance from the nucleus grows, what is going to be the effect of the nucleus on those electrons? Do what? Harder to hold on to them. You with me? Okay. The number of core electrons. What if I now... All right, so we started with sodium. Let's go all the way down to cesium. Cesium is number 55. What if I take 54 kindergartners and get them running around you? What's the chance of you missing one? None. You're not even going to realize that little one's gone. Okay? So again, if I take it and I expand that area, so the distance and the number is drastically going to change how you're going to manipulate the nucleus. So this slide right here is very important. Put a big, huge star up here in the corner. And we're going to add one little sentence to it. Okay, so as the average number of screening electrons increase, what happens to your ZEF? It decreases. So the more you have, the harder it is to hold on. Does that make sense? The second thing is, as the distance from the nucleus increases, what happens to ZEF? It also decreases. Excuse me, as the distance increases, ZEF decreases. So here's what I want you to do. So our core electrons and distance come on, it's not even fun writing on this thing anymore. Are related how to ZEF? What? Inversely or indirectly? Okay, give me just 1 second. I'll show it, okay? Are inversely related okay. All right, to answer your question was, what is ZEF actually measuring, right? Okay. ZEF is calculatable. It has a number. It has a quantity. We're not going to calculate it. We're not going to do any of that. But what it's measuring is the ability of the nucleus to maintain a effective grasp or an effective attraction between the nucleus and all of the electrons. Okay? The higher the ZEF, the stronger the bonds and the attraction of the nucleus and all the electrons. Okay? And we're going to see in just a minute how ZEF increases or decreasing according to the periodic table. We're going to look at that in just a second. Okay? So this is what I want you to know, is that these things are inversely related. So as the size gets bigger, what happens to your ZEF? It's got to get less. Okay? Well, what happens as the atom gets smaller? It's got to go up because it's going to be able to hold it in a little bit tighter. And I promise you we're going to see an example in just a minute. First period got it as soon as we saw that little clip. Now, you know, I don't think they got a whole lot out of this, so I'm just going to skip that. argon atoms. Argon. What group is argon in? Very good. This is a noble gas. Can anybody see what number it is? Very good. It's 18. So noble gas, argon, has 18 electrons. And this is what we're going to do. What does it mean to undergo collisions? Collide. So what we're going to do is we're going to take two argon atoms and we're going to slam them into each other. Okay? Here's what's going to happen. Or you tell me what is going to happen to those things. Are they going to stick or are they going to bounce? They're going to bounce. Do you agree that at one moment in time, that when those two things collide, there is a distance at which they are the closest in terms of the nucleus? Everybody with me? There's a point at which those two nuclei are the closest they can possibly be. So here's what's going to happen when they collide. They're going to ricochet. What is ricochet? Bounce off. They're going to bounce apart because, and here's why, the electron clouds cannot penetrate each other. Why can the electron clouds not penetrate each other? Same charge. Very good. The reason why is because we have the same charge. They're both what? They're both negative. Okay? Imagine if we could somehow suspend a ping pong ball in the middle of a basketball. Just pretend that that's possible. Okay? If I threw those two basketballs up against each other, would the ping pong balls ever hit? No. Why? What are the two basketballs going to do? They're going to bounce off of each other before the nuclei ever get to each other. So that's essentially what's happening here. The apparent radius. So let's talk about this. Radius. What is radius? Half the distance. Okay. The apparent radius is determined by the closest distance separating the nuclei. So when will we determine the radii of an atom? And here's the, go ahead. When they're the closest together. So here's the little picture that I want to create. Yeah, this will actually work. I couldn't get it to work out just right, but it'll still, hopefully it'll still make sense. Pretend that these two spheres are the exact same size. Okay? Let's just pretend that they're basketballs. Can I find the exact center point of both of these spheres? Okay? Again, I'm not perfect, but I'm going to try to make it be as best I can. So we're going to take that, and we're going to say right there. That's about as good as it's going to get. For these spheres, could I find the exact radius? Yes. How? Measure from there and measure from there. Do you agree that I could get a radius there and a radius there? Huh? What's the problem if these two things are atoms? Do you have any idea where that end point is? No. So here's what we got to do. We got to make these two things collide. Okay? Well, when they do, this is what we're going to do. Do you agree I could then find the exact total distance between these two? Yes. So I'm going to have a distance. How would I find the radius now? So I would do d divided by 2. Is that right? And that would give me the atomic radius. Okay, that makes sense. So again, when I start talking about the distances between atoms, how large the atomic radius is, and you're going to see this in just a second, how large it is. First of all, hint, hint, wink, wink, you need to know this. Its unit is the picometer, and the prefix pico equals 1 times 10 to the negative 12th. That's 1 trillionth of a meter. This is a meter. It's a trillionth of this thing. If that makes any sense at all, which it probably shouldn't. That's how small it is. Okay? So again, that's what we're going to have to do to those. These are sometimes also called van der Waals radii or non-bonding radii. I went in to spend a moment just for this right here. Consider simple diatomic molecule. I'm forewarning you right now, there are 7 of these that you have to memorize. If you don't, you will not pass this class. 7. Okay, and I'm going to give you a hint in just a second. But let's talk about what a diatomic is. What does the prefix di mean? 2, atomic means atom. So what is a diatomic molecule? 2 atoms. Okay. Here are the 7. I want you to add a page, and I want you to write these down, just like I have them. Okay. Add a page and write that down for me. Yes. Okay, so here are the 7 diatomics. You've got these 3 and then these 4. Now, I've given you 2 tips. One of them, they all end in gen. So start right here. What are these 3? And then fluorine, chlorine, bromine. Wait a minute. What do I mean by they all end in gen? What are these? Say it again. These are the halogens. So, hydrogen, nitrogen, oxygen, and the halogens. So here's what a diatomic is, and this is the concept that I need you to understand. You will never, ever, 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 ever write these elements by themselves. They always come in twos. They have a twin. They're never going to be separated. Now let me ask you something, because I always get this question. Is H plus and H2 the same thing? No, it's not. This is okay, because this is not the hydrogen atom. This is the hydrogen what? Ion. It's completely different. But you will never write just H by itself, nor the rest of them. Now let me show you the other version called the gun and the bullet. And I come up with this a few years ago, and most of the students like this one better because it shows you on the periodic table which ones they are. Okay? Let's see. So, what does that kind of look like? Hence the gun. Kind of looks like a gun, right? I mean, kind of looks like a gun. I mean, or we're so gangster we can turn it upside down and shoot. Okay? But what am I missing? There's your bullet. Okay? Those are your 7. Okay? What? It's a different angle. Or you're shooting upside down and it goes up. But again, the whole point is just for you to remember these. So if you ever see these, so I used to say 6 of them make a 7. See that? 6 of them make a 7. But everybody always forgot about the hydrogen. So I had to add the bullet. So I changed it to a gun and a bullet. Yes, sir. No. That's exactly what we breathe. Yes, we don't breathe the letter O. We breathe O2. You won't. Huh? Hang on a second. Let's see. What is that? What do we breathe out? What else do we breathe out? What do we breathe in? You ever seen that formula? What is that? Cellular respiration. So it's not O. It's O what? It's O2. That's why. Okay. If I flip this equation over, what have I just done? Photosynthesis. Photosynthesis and cellular respiration are the exact same thing. They're just what? They're just backwards. The easy way to remember, what do plants need? They need water. What else do they need? Carbon dioxide. And what do they make? Oxygen and glucose. It's the same thing, just flipped over. So again, you've seen this how many times? And you've never asked the question, why is it O2? The reason why it's O2 is because it's a diatomic. And I really wish they would explain that to you back in 7th grade, 9th grade. There's a reason why it is O2. That's a great question. All right. This is oxygen. Really wish. How many's the first orbital hold? 2. Sorry. Electron here. Electron here, right? Okay. The second orbital can hold how many? Tell you what. Let's check. Let's do this. Y'all know this. All right. You ever heard of Lewis dot? We're going to get into it. Lewis dot shows valence electrons. How many valence electrons does oxygen have? How many? 6. 1, 2, 3, 4, 5, 6. Everybody with me? How many empty spots does it have? 2. Here and here. We there? That makes sense? All right. So here's what we can have. If we take another oxygen, 1, 2. Start over. 1, 2, 3, 4, 5, 6. How many empty spaces does it have? 2, right? I'm going to redraw this, and I'm going to move the electrons around for just a second. So this is the new version. So we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So how many do both of them need? 2. Well, here's what you can do. You can take 2 of these, and you can share them back and forth. So they both have 8. Okay. So it's stable. So what you are creating is a double bonded oxygen. One line equals 2 electrons. Every atom has to have how many to be stable? 8. 2, 4, 6, 8. 2, 4, 6, 8. Everything's stable. Okay. If you did it with hydrogen, how many does it need? It just needs 2. Well, if you share these back and forth, they both got 2. So it's a stable bond. And you could do it with nitrogen. Nitrogen needs would have to have a triple bond. And again, we'll get into all this. Yep, the diatomics are the only ones that work that way. Any of the halogens, if you did fluorine, 1, 2, 3, 4, 5, 6, you put 1 in the middle. So you got 2, 4, 6, 8, 2, 4, 6, 8. So any of the halogens have a single bond, just like that. And again, we'll get into all of this, but that's a good question. That's why that they pair up. It's because they're more stable in that form. Okay, great question. All right. What are you doing? Okay. All right, so again, this is what we were talking about just a second ago. If the 2 atoms are the same, 2 atoms are the same, first of all, what do we call it? Call it a diatomic. Okay, how many of them are there? There are 7 of them. We call this the covalent radius, the bonding. So, right here, do you agree that those 2 black circles are the nuclei? Why can we not know exactly where that atom ends? Because the electrons, it's a cloud. We're not quite sure. But if we take the entire distance, how do we find how large one radius is? Just half the distance. Okay, that's how we do it. All right, so here's what we're going to do. We're going to go into something called the Zeph tutorial. This is what I need you to do. I need you to pull over the, go into Schoology real quick, and it's the second one in Chapter 5. It says Zeph tutorial. Okay, here we go.
Let's start off with a question. Based on information in the periodic table, which do you think is bigger, Na or Mg?
Okay, so here's what I want you to do. I want you to write on this slide which one of those 2 that you think is larger, and then tell me why you think it is larger. Okay? Na or Mg? There's not a wrong answer yet. Because right now, you don't have a foundational knowledge of any of this stuff. By the end, it should all make sense. Come up with something, yeah. Come up with something. Chemistry, there's no easy answer. Yeah, just right on the slide. No, in terms of how large the radius is. Which one has a larger radius? Don't look up there. Okay, I'm just taking a quick poll. I don't care who says what. I'm just curious. How many of you say NA? Okay, how many of you say MG? All right. If you said NA, why did you say NA? And you don't count. Who said NA? Why'd you say? No, I'm not. I can't just ask. Well, why'd you pick NA? Okay, why did you pick NA? Okay, the mass is less, so you think it's bigger. Okay, somebody else picked NA. Who else was it? Besides Nick. Did you? Okay, why'd you pick NA? Okay, alright, we'll go with that. Alright, so here, stop. Stop. Alright, here we go. Okay. Alright, so those of you that picked MG, which was the majority of you, did anybody say because it has more protons? Okay, or had a higher atomic number? Okay. Alright, well, in the atomic number protons? Okay, alright, so, again, keep that in mind. Do you agree that that is true, that last little part? That both of these are 3s1 and 3s2. So they're going to fill that exact same orbital. Okay, did anybody say MG was bigger because it has more electrons? Okay, all right.
So perhaps this led you to predict that because they both have the same number of occupied electron energy levels, the two atoms should be the same size.
Did anybody say same size? Okay, so again, the reason she said same size is because, again, they're on the exact same energy level. They're both in the 3s. Well, let's keep reading.
That may be closer to the truth. But remember that each atom has its own unique spacing of the energy levels. So let's learn more about the forces at play before we draw any conclusions. Let's consider a lithium atom. Since its atomic number is 3, we know it has 3 protons in the nucleus.
Is that true or false? That's true. Alright, so do you see the little diagram? Y'all probably need to look at the board because it's going to make more sense. Because you're looking at the entire completed PowerPoint. He's going to pop things up there as he goes along. So if y'all just look up here. Okay, so do you agree that that's true for the nucleus? What's he not showing that really doesn't matter? Neutrons. They don't have any effect here.
This means that its nucleus has a charge of 3 positive.
Pause on what you're thinking. It said the nucleus is 3 positive. Is that true? Yes, the nucleus is.
And Li's electron configuration is 1s2, 2s1.
Is that true? Yes.
This means it has 2 electrons in the first energy level, 1s2.
Okay. So when you pop this up there, is that now true? Why is that true? The first one always holds what? 2. What group is lithium in? Group 1. So how many valence electrons should it have? Should have 1. We've already used, it had 3 to begin with. We've already used 2. So how many should be in the second orbital? 1. Well, how many's left in our configuration? 1. So that should make sense here. So let's look what he talks about next. Which is true. Which is what we have here.
So this is what Li's Bohr diagram would look like.
Okay, this is true.
Now let's consider how much each electron is attracted by the nucleus.
Okay, so let's think about this before he begins. Again, we're out there on the playground with a bunch of kindergartners. You've got, let's just pretend you have 3 eyes, or you're one person, and you have 2 that are the closest to you. Do you think the 2 or the 1 is the most attracted by the nucleus? The 2 closest to it, right? Because you can hold on to those a little bit closer.
First, the 2 electrons on the lowest level. Since they have no electrons charge pulling them in toward the nucleus. For these two electrons, the effective nuclear charge, Z star, is 3 positive.
All right, so what he's saying is that Z star is Zeph. Instead of writing the little EFF, he puts Z star. So what he's saying is that these two electrons have the full attraction by what? How many in the nucleus? 3. So we have a 3 on 2 right now. Do you agree? All right. So the reason why is because there's nothing in between them. Well, what do you think happens when we move out to the next level? What's wrong? There's something in between. What do we call that when there's something in between? Shielding or screening. So this is what we're going to get into something called electron shielding. So, do you agree that the Zeph is 3 positive? You have 3 protons attracting 2. So it's going to be 3.
Now, what about the 1 electron on the second level? Beneath it, there are 2 electrons that act as shielded from the charge on the nucleus. Thus, this electron only feels a charge of 1 positive pulling in toward the nucleus. For this outermost electron, Z star equals 1 positive.
All right, so here's what I want you to do. I want you to highlight 2 electrons that act to shield it from the charge on the nucleus. So, essentially what has happened is that these 2 electrons have occupied what? 2 of the protons, right? So what does that mean? Now you're only working with 1-on-1. So we have 1 proton trying to hold on to that 1 electron. Go ahead. Yes. It was all 3. Now we're counting the number of protons that can affect it. The second one, there's only 1 proton affecting it. Because it's 3 protons are affecting both of those. Now on the second level, those 2 cancel out 2 of them. So you only have 1 left over. Okay? Because it's only 1 positive because there's 1 electron. Yep. Okay? All right.
In other words, these 2 electrons come between the 3 positive nucleus and the outermost electron.
So what would your total Zeph be? What is 1 plus 3? 4. Keep that in mind as we go along. Do me a favor, underneath 3 plus and 1 plus and 3 plus, add a little equal line and write the number 4, please. Mac, you with me? You sure? Okay.
These 2 electrons effectively cancel out 2 of the protons.
Okay, so that's essentially, that's kind of the picture y'all see, right? Okay.
And this leaves just 1 proton to attract the outermost electron. So the effective nuclear charge felt by the outermost electron is only 1 positive.
All right.
This blocking out of the nuclear charge by lower level electrons is known as shielding.
All right, highlight that very bottom sentence for me. This blocking out of the nuclear charge by the lower level electrons is known as shielding. Now, do you agree that this atom only has 2 orbitals? What happens when this thing starts to get bigger and bigger and bigger, and there's more and more and more things in the way? What's going to happen to your Zeph? If I take you out there and send 54 kindergartners running around at your feet, what's going to happen? It's going to be harder and harder and harder to hold on to that 1. Right? So what's got to happen to your Zeph? It's got to go down. So remember earlier we talked about the number of core electrons and your distance. As those things go up, what happens to your Zeph? Zeph has to go down because they're inversely related. All right, let's keep watching.
Now let's consider Bohr diagrams for the next 2 elements on the periodic table, Be and D. How many protons do they each have in their nuclei? Write down your predictions for me.
Okay? Be, what element number is Be? It's beryllium, so it's number 4. So it's got 4 protons. What about boron? It's number 5, so it's got 5 protons. So we've got 4 in here and 5 in here.
Write them down before continuing.
You should have that on there. But what is beryllium's electron configuration? Very good. 1s2, 2s2. All right, what about boron? 1s2, 2s2, and then 2p1. Very good.
Is this what you wrote down?
All right, those pop up at the bottom.
And so what would their Bohr diagram look like? Write them down.
Okay, how many would be on the first ring around beryllium? 2. How many would be on the second ring around beryllium? Wasn't that all 4 of them? So you're done. All right, now let's move on to boron. You've got 2 on the first. How many on the second one? 3. Very good. So there you go. Now, let's pause for just a second. Let's talk about why these aren't quite the best drawings. What's wrong with those red dots? They're too close to each other. What would they really be doing? They're going to repelling. But for this example, it works out just right.
And finally, what effective nuclear charges will be experienced by each of these electrons? Write them down before we
All right, so here's what I want you to do. I want you to write on either end which one would have the highest Zeph and which end would have the lowest Zeph. And what I mean by that is how much effect that nucleus has on that outermost ring. You can be right, you can be wrong right now. You don't have the foundation to build upon this yet. But write H for highest and L for lowest by which end you think has the highest Zeph and the lowest Zeph. Remember, Zeph is you being able to hold on to everything that's present. So if I send you out there with 10 kids, you're going to come back with all 10 kids. Okay, just out of curiosity, how many of you put H on the left? Okay, how many of you put it on the right? Okay, the highest Zeph on the right for boron. Okay, we'll keep that in mind. Let's keep getting.
Is this what you had?
Okay, so now do you see these numbers? So here's what I want you to do. What would be 2 plus 4? 6. Add that underneath there. What is 3 plus 5? 8. Which one has the highest Zeph? Boron. What's wrong? The hold is stronger. It is. It's going to explain it in the next slide. I promise we'll go through. Okay, sir. Okay, you're counting the electrons. You can't count the electrons. You have to count the protons. Is there anything in between these? So how many of these protons can hold on to those electrons? All 3 of them. However, when you try to go to that third level, is there anything in between those? There's 2 of those. So these 2 are going to suck up those 2 protons, so they can't get to it. So there's only 1 proton left to get out there to that one to hold on to it. So if we move over, is there anything in between those? So all 4 of these protons are going to be attracted to that, right? Well, now, what happens when you move to the second level? What's wrong? These 2 are absorbed by those 2. Well, so you only have 2 left. One more time. Is there anything between those? So you have all 5 holding on. Well, then what happens is your second ring, when you've got 3 of them trying to hold on, well, these 2 absorb those 2. So how many do you have left? You've only got 3 left. Yes, sir. You're ahead of me, but I'm going to say yes. Yes. You're ahead of me, but yes. Okay? All right, so let's continue to listen to it.
So what do these Bohr diagrams and effective nuclear charges tell us about these atoms? First, compared to Li, these electrons are being pulled in with a stronger charge, both at the first level and the second.
Okay, one more time. Compared to Li, Be's electrons are being pulled with a stronger charge. Remember how we counted it? This one was 4 and this one was 6. So Be's holding on a little bit stronger.
This stronger attractive force would actually pull these levels in closer to the nucleus.
Highlight that statement. That's very, very, very important. Very important that you get that. Get that? Fine. You sure? What did you highlight? Make sure you're in this. Okay? The stronger the attractive force, would act to pull these levels closer to the nucleus. So what does that tell us about the distance in relationship to Zeph? The higher the Zeph, the closer the distance, or the lower the distance is. Okay?
This means that BE is actually smaller than Li. One way to describe how big atoms are is by the atomic radius, the distance from the nucleus to the outermost electrons.
Okay? So, did you notice how BE just got a little bit smaller? Okay? Why did it get smaller? What was higher? The Zeph was higher.
Li's atomic radius is 145 picometers, while BE's is only 105 picometers. A picometer is a trillionth of a meter.
Remember I told you a minute ago the unit was the picometer? So it was 145 and it went down to 105. So how much did it shrink by? 40. It went down by 40 picometers, so it is a little bit smaller.
Now, how would B's size compare with the other two? Make a prediction, number 6, and explain why.
So what do you think would happen? It's going to be smaller. Why is it going to be smaller in B than it is in BE? Zeph is higher. Do you agree that there's more effective nuclear charge? There's more of a nucleus to hold those things in? Okay, so the Zeph has to go up, so it's got to get a little bit smaller. Did it get smaller?
Is this what you predicted?
Okay.
And did you explain that B should be smaller than either Li or BE because it has the greatest effective nuclear charge, Z star, pulling its electrons in?
Okay, that's what's going on there.
If Li's atomic radius is 145 picometers and BE's is 105 picometers, make a guess as to what B's atomic radius might be.
What do you think it would be? What? How much did it drop by? 40, so what do you think the other one's, what is it going to be? 85. Okay. Why is it 85? It's dropping by 40. Okay.
Were you close?
105 minus 85. Excuse me, 105 minus 40 is 85. No. Okay. So it's yeah, it's going okay.
And
Yeah, my bad.
getting smaller and smaller as you move to
I wasn't thinking.
across the entire periodic table.
Okay. So notice what happens. Do you see this picture? What's happening as we move from group 1, and I want you to add this group 1 all the way to group 18. They're getting what? Smaller. Add this, please. So as we move this way, they're getting smaller. So since they're getting smaller, what does that tell me about my Zeph? Very good, it's increasing. Now, we're going to talk about ionization energy in just a minute. Matter of fact, we may stop at this point. But if I wanted to come in and take an electron based on size only, which one would be more difficult to take? Why neon? Based on size only, it's the smallest. Is there one other thing you could talk about the Zeph? Why would we talk about Zeph? Zeph is the highest. Well, what else do we know about neon? It's noble gas. Do noble gases react at all? Nope. So that also has to make sense trend-wise. There's one last thing.
But what happens after NE?
All right, we'll stop there. No. We got like 20 more minutes, don't we? Yes, we do. Yeah, we got to 137. Or one. I'm looking at the wrong number. No, I've got 10 more minutes. I'm sorry.
NE's Bohr diagram looks like this.
Okay. Now we're talking about neon. What do we know about the outer ring of neon? It's full. It's stable.
With a 10 positive charge in the nucleus, an effective nuclear charge of 10 positive, 8 positive, pulling the electrons in very close. After Ne comes Na. Predict what Na's Bohr diagram would look like. Number 8.
Okay. How many electrons does neon or sodium have? 11. So, can we fit any more red dots on that second ring? So what are we going to have to do? Add another ring.
After Ne comes Na. It has an electron configuration 1s2, 2s2, 2p6, 3s1. Neon, 3s1. Which means it has all the same electrons as Na, plus one more electron in the third level.
If you did not know how to draw this, how could you have already known that it has one more in the third level either way? It's what? It's group 1. What do we know about group 1? They have one valence electron, so all these things should make sense.
Is this what you predicted?
So again, you've got 2, 8, and then 1. Is it slightly larger? Why? It's got an extra orbital.
And now predict what the Z star values will be for each level. Number 9.
Okay? The first ring would be 11 on 2, right? So you've got 11. How many protons would affect the second ring? 9. Very good. Why 9? Because the first 2 cancel it out, right? But here's the difference. How many would be able to attract to that last one? Just 1. Why? Because the 10 core electrons cancel out 10 of the protons. So how many's left? 1. So we've got 1 on 1. And did it get a little bit larger? So it's going to be a little bit harder to hold on to it.
Is this what you were thinking?
So 11, 9, and 1.
And what would you predict for the size of an Na atom?
Is it larger or smaller than sodium?
Its outermost electron is only being held in place with a very weak, one positive effective nuclear charge. So how far out do you think that valence outermost level would be? Number 10.
Okay. So watch what happens. What did it do?
Is this what you were picturing?
Did it jump way out there? So notice what happened. Notice the picometer. Anybody remember what lithium was? No, the picometers. It was 145. Well, notice what sodium is. 180. So is sodium bigger than lithium? Yes, but notice what just happens.
Placing these back into the series,
Do you see something weird? It get really, really small, and then what happened? Got bigger again. Well, let's see if we can fix that.
shows an obvious break in the trend for this period. Thus, it would seem to make more sense to have Na start a new period.
Does that look kind of familiar to up there? What's under Li? Here's why.
After all, Na does have just one valence electron, just like Li, and has a large radius, just like Li. In fact, Na is bigger. Write down your prediction as to why you think Na is bigger than Li.
Okay, why do you think it is larger? It's got more electrons, it's got more orbitals, so it's got to be a little bit larger.
Did you say that Na is bigger because it has a whole extra level compared to Li? If so, good job. But what happens next?
What is that whole extra level really in chemistry? It's an orbital, right? We're adding an orbital to it.
After Na is Mg, which has 2 electrons in its valence element, just like Be, each of which experiences a Z star of 2 positive, just like Be.
Does anyone remember the original question before we ever began? What's bigger, Na or? What's the answer? Na is bigger. Now that you see that, why? Zeph is higher. Therefore, the atom is smaller. That's the whole reason.
This would make Mg smaller than Na, just as Be was smaller than Li. After that, the pattern continues for period 3, just as it did for period 2.
So you notice as it's going across, it's getting smaller. Okay?
Notice how as you go left to right across the periodic table, the atomic radius steadily decreases.
All right, find this, and I want you to highlight that entire first little block up there, please, in one color. Pick one color and highlight that entire first thing. As you go left to right across the periodic table, the atomic radius steadily does what? Decreases. Very good. Okay? So that arrow, do y'all see that on y'all's? Okay?
And as you move down the periodic table, the atomic radius gradually increases.
Alright, I want you to highlight that in a different color. So as you go down, what happens to the atoms? They get larger. So, yes, we're talking about the size, but I want you to come in and add this. As I move left to right, what has to happen to Zeph for them to get smaller? It's got to go up. Okay? As they go down, what has to happen? Zeph has to also go down. So, it's going to get larger, larger, larger. Okay? And we'll stop there for today.